Hey there and hello. My name is James with Tektronix. I'll be the host for today's session on Sensor Measurements 101, which is part of a longer series of Measurements 101. If you registered for this event, then you're registered for the other webinars, which means you have access to the on-demand versions of ones we've presented, as well as the ones that are coming up. If you're watching on YouTube, we'll drop a link to that registration in chat if you want to sign up for that. Before we get started, a couple of housekeeping options. Number one, you can use the chat tab to chat with fellow attendees as well as myself. And you can start out by letting us know where you're watching from today. And then the second is that if you have a question for our presenter, please use the questions tab to send those questions to us so that we can make sure that she sees them. Speaking of presenter, our presenter today is Liz Makeley, and she's an applications engineer here at Tektronix. With that, take it away, Liz.
Hi everyone, welcome. My name is Liz Makeley. I'm an applications engineer here with Keithley Instruments. I specialize in DMMs, DAC, switching, and sensitive products, and I'm here today to talk about a fun topic in the test and measurement world, which is the use of sensors. Before we get started, here's an agenda for the session. We'll start with covering what a sensor is and an overview of how they work, and then we'll take a look at several examples of common sensors and how each of them work. Finally, we'll cover how to choose a sensor for your application and how to set up your system to take measurements. So that is a lot to cover in a short session. We will dive right in. A sensor is simply a device that measures something about the world around us. There are a lot of properties about our environment that are very difficult to measure directly. The easiest example I can probably give is temperature. We can physically feel a temperature difference on our skin, but what feels warm to me might feel cooler to someone else. We can't see or touch temperature and know what the temperature is as a property. The same thing goes for properties like pressure, chemical composition, sound volume. None of these are things we can quantify just by looking at it or touching it, or measuring it like we could, say, size with a ruler. So we have to use a sensor. A sensor detects changes in a physical property and reacts in a way that we actually can quantify. The key with this is that we need to know the relationship between the two. A metal pot gets hot when it comes in contact with a flame, but that reaction is not something we can quantify, so it's not useful. I find it's best to explain this whole concept with an example. Most people are familiar with mercury thermometers, even though digital ones are much more common now. In that case, the property we're trying to measure is temperature, and the reaction to the change in temperature is a change in the size of the mercury. And with the thermometer, we've built this in a way that we know exactly how much mercury is expanding, and we can measure the temperature in regards to the height of the mercury in the tube. Another really good example is an anemometer, which measures wind speed. The cups at the top catch the wind and spin, and we can count the number of revolutions over a certain time period, so that's rotational speed, and we can use that to calculate the speed of the wind. So the type of sensor we're using determines how we're measuring the property. Sensors can change physically by changing their size, speed, or position. There could be a change in material property, the most common example being like a change in resistance. The sensor may produce a change in electrical signal, and we can measure a voltage or a current output. Once we know what the output is that we're trying to measure, we can choose the appropriate tool to measure the reaction, whether that's just a simple ruler or something more complex like a digital multimeter. The key with sensors is that what we're measuring isn't technically the value we want. So we always have to remember we're measuring the relationship between these two properties, and we're going to have to convert any data we get back to the property we actually want. Typically this relationship is specified in the data sheet, but I'll talk more about that later. With this discussion on sensor outputs, I think it's important to do a little bit of a definition talk here. If you're familiar with sensors in the test and measurement space, you may have come across the term transducer before. And there's actually a little bit of a disagreement on the overlap between sensors and transducers, but I think fundamentally we can define, for this discussion, a sensor as something that's measuring a property via another property. The relationship between these two properties doesn't have to be electrical in nature, but we can measure it using electrical measurements. We'll see an example of this when we talk about thermistors and RTDs. But often, when the property change is electrical in nature, so we're looking at generating a current or a voltage, that's more in the transducer category. So a transducer is a device that is converting energy from one type to another. And we can split this category into two subcategories, which would be input transducers, which is taking some input energy and transforming it into something else. Typically, that something else is electrical in nature, and we can categorize those as sensors. That's where the overlap is with sensors. So those examples in the center, that Venn diagram, the thermocouple, pH probe, all of those are generating a voltage with respect to the input. And then the other category would be output transducers or actuators, which is typically converting electrical energy into some other form. So, for example, I have the speaker. So we're taking in an electrical signal, we are producing a sound wave, and typically these aren't used for measurement. So that it's just outputting a different form of energy. For the purposes of this discussion, we're going to focus on anything that measures something, aka anything that we would count as a sensor, whether or not it could be categorized as a transducer. And we're also going to only focus on sensors that require electrical measurement, either because they produce an electrical signal or they change some property that we measure electrically, like resistance. So that's not to say that other types of sensors aren't actually sensors. A mercury thermometer is a type of sensor, but there's no point in having a discussion about electrical measurements with them. So now that we've got an idea of what a sensor is, let's take a deeper look at some types of sensors and how they work. I think maybe the most common type of sensor that a lot of engineers would work with on a daily basis is a temperature sensor. Honestly, even if you're not an engineer, you interact with temperature sensors every single day without even realizing it. Any kind of digital temperature reading device is using a sensor to measure the temperature. There's temperature sensors in your cars, in your ovens, your computers, any electronics that would generate their own heat, and we need a mechanism to cool them. We're going to have a temperature sensor in there to monitor the temperature, to let us know whether or not we need to engage that cooling system, or whether or not your phone needs to say I'm overheating, and to take a break with it. So they are very common. We see them everywhere. In the test and measurement industry in particular, we see temperature measurements all the time as part of environmental testing, as part of stress testing, where we're looking to expose devices to extreme conditions to verify functionality or age the device. We can use them to directly measure a device's heating and cooling behavior as we use it. And sometimes we design sensors into other systems. So like going back to my car example, we're designing those sensors to be in the car engine. So we may want to validate that that system is working correctly by having a separate calibrated measurement tool to double check our values. So what kinds of temperature sensors are there? The thermocouple is probably the most common temperature sensor. They work by converting temperature to a voltage difference using something called the Seebeck effect. So the Seebeck effect is when we have two dissimilar metals that are connected together at one end. So I have a thermocouple right here, connected together at one end, and then it's exposed to a temperature gradient. So we have a gradient between this end and this end, which is disconnected. And this disconnected end we're calling the cold junction or the reference junction for the thermocouple. If we know the temperature at this end, we can calculate the temperature at this end using an equation or a lookup table, and then we have our temperature. Thermocouples are pretty universal, they're cheap, they're easy to use, there's lots of types that combine different types of metals for a range of temperature values, and they're pretty fast to react. So I have my thermocouple connected to my DMM here. I can press it and get a change in my reading pretty quickly. So they are a a good common tool to measure temperature, but they aren't always as accurate as some of the other types of sensors out there. So for example, a thermistor would be kind of the next level of temperature sensor because they're more accurate than thermocouples, but they're a little slower to react and have a little bit more of a limited range of temperatures that they work for compared to some other sensors. They work by using a metal oxide material that changes resistance with temperature. So depending on the material, that change could be negative, i.e. the resistance is decreasing while the temperature is increasing, or it could be positive where the temperature increases and the resistance increases. Thermistors are a good example of that kind of blur between sensors and transducers because technically we're not changing energy types here. The thermal energy just causes a change in the physical property of the material, and that physical property we just happen to be able to measure using an electrical measurement. But we're not generating any electrical energy here. For thermistors, we relate the resistance back to temperature using a third order equation called the Steinhart-Hart equation, which allows us to get a wider accuracy range than if we just approximated the thermistor to be linear, like with Ohm's law. So that is how we use that. The last type of temperature sensor that I'll talk about is an RTD, or a resistance temperature detector. RTDs change in resistance like thermistors do, but the difference is that they use a pure metal coil, which means that they're a little more linear and a little more stable than thermistors. RTDs are typically specified by their base resistance at 0 degrees. So if you had a PT100, that would be a platinum metal that is a 100 ohms at 0 degrees Celsius. Usually for RTDs, we specify a temperature coefficient and a tolerance. The construction for RTDs is much more precise than that of thermocouples and thermistors, so we can actually be very accurate with them. They also can come in 3 and 4 wire options. So I have an RTD here that's got 3 wires connected to it, so that we can eliminate lead resistance, improving our accuracy. Because of the high accuracy and durability, RTDs are often used for very extreme test conditions and critical applications where we need an accurate sensor that isn't likely to go bad over time. But the biggest downside is that they are very slow. It can take several seconds for an RTD to settle after a temperature change. So if your application has potential for quick temperature spikes, or you need a really fast result, and you're not too concerned about the accuracy, you're going to want to go with a thermocouple or a thermistor over the RTD. So strain gauges are used to measure changes in physical force that cause strain on an object. For a large scale example, if we built a skyscraper, storms and wind can cause strain on the materials in that building, and measuring strain on the materials can help give us an idea of areas for structural damage. Strain gauges are commonly used to measure torque in motors, strain on any load-bearing parts in applications like aerospace applications and railway things. So they work by using a conductive foil structure and a flexible back. So in that image there on the right, you can see the sort of squiggly looking lines. That is the resistive foil that conducts, and then it's placed on that flexible back. This back is able to stretch and compress with the material that we're measuring. The resistance of the conductive foil then increases and decreases respectively. Typically, we measure these with a resistor configuration called a Wheatstone bridge, which generates a voltage output with respect to how the resistance of the strain gauge is changing. But this is complicated. It requires math to figure out what the actual resistance or the actual strain value is. And it was much simpler just to use a DMM to measure the resistance directly. And we can do this using the gauge factor, which is typically specified for a device, and a starting value, which we would typically take as the resistance when it is unstrained. To calculate the strain directly. We have an application note on our website about how to do this, and I have that linked in the references. So light is something that we don't often think about measuring, but sensing light is becoming super critical with the rise in optical communication like fiber optics. To measure light, we have to use a photosensor or photodetector, which is a broad category of devices. There's lots of ways we can do this, that converts light waves or EM waves to some measurable stimulus. A really basic example would be the photodiode, which generates a current when it's exposed to light. The basis of this and some other photoconductive devices like phototransistors is the p-n junction. When the light hits the junction, electrons separate from the material, creating free electrons and then holes where those electrons previously were, and those electrons are now free to jump from hole to hole, which is a measurable current. This principle can be extended to, like I said, phototransistors, or we can use a metal semiconductor junction for a Schottky design, which gives us better response time. There are tons of other types of photosensors, considering that but the considerations that we have to make when we choose one is pretty much the same. We're looking at things like the spectral response, which is what types of frequencies will cause a response in the detector. If we want to measure visual light, it's not helpful to have a detector that only measures infrared light. So that's important. The responsivity, how much current is generated with respect to the power of the light. So that helps us understand how sensitive our measurement is going to be. How much light do we have to apply to get a measurable response? The dark current, how much current is flowing when there is no light applied. This is kind of like the error in it. And then also the response time, how quickly the sensor responds to a stimulus. And this is especially important for optical communications because we don't want to miss information, nor do we want slow communication just because our detector is not able to run fast enough or react fast enough. So BioFETs, I think, are some of the coolest sensors. They use materials such as bioreceptors, membranes, and nanomaterials to detect the presence of some other material in a sample called the analyte. If this analyte is present, the characteristic behavior of the FET will then change. So for example, if we have a really high concentration of some virus in a sample of fluid, we may see the FET conduct more current across the drain source channel than if there were no viruses present in the sample. Chemical FETs kind of work under the same principles, that the presence of some chemical that we're testing for will then change the behavior of the device, and we can measure using the IV characteristic curve. Of course, that means we need to have proper equipment for IV characterization, which often means having equipment that can do lower current measurements or multiple channels. So we're looking at equipment like source measure units or a full parameter analyzer. Those types of things are best for these measurements. If you would like to learn more about IV characterization and some basic tips for it, I highly recommend checking out our IV Characterization 101 course, where I demonstrate some MOSFET characterization. So that is a very short list of all the possible sensors out there, but hopefully that sparked your imagination on how you could achieve your measurement. So now for the important part, how do we get started with our sensor measurement? I personally love step-by-step instructions, and I try to break down any measurement problem into step-by-steps. And a lot of time I find that step one is always the same, which is what the heck are we measuring? Because that determines everything else about our system. You wouldn't consider a thermocouple to measure something other than temperature. So we need to know what property we are trying to measure with the sensor to determine where to even start looking at our sensor options. Once we've narrowed down our choices to the sensors that are actually doing what we want them to, we need to choose our sensor. There are lots of questions you can ask yourself to help choose, but at a minimum, these are the ones you would ask for kind of any general sensor. You should look at what accuracy you need. Some sensors perform better than others. Some sensors are capable of getting lower resolution. So if you're just doing a quick spot check on something, you can go with something that's cheap and easy to use. But if you need something that is very critical, that you need really small resolution data in, that you want to see very small changes, you're going to want to find a sensor that performs that well. I have talked about response time a lot here, but it really is a very crucial factor for sensors because no matter what, it takes time for the output stimulus to reach the sensor, for the sensor material to react, and then produce that output, and then for us to measure it. So if you're trying to measure something that has very quick changes, you're going to be limited by how fast your sensor can react. So it's a really, really important factor to consider. The conditions that you're measuring, the maximum and minimum conditions, are important because if you get a sensor that isn't rated for what you're trying to measure, it's useless. If I get a sensor that only goes up to 200 degrees C, I can't measure my 500 degrees C application. So that is a critical thing to consider. Also consider how properties of the sensor might change as you're using it. If you're using it as part of a larger circuit, how does the behavior of the device react with the circuit? And then finally, form factor actually is an important consideration. So I have my thermocouple here. You can see it's basically just a wire. The tip of this can be as big or small as we need, but with an RTD, I have to have this full coil on this ceramic or glass core. This is a very large difference in size. So if I'm working in a place where I only have a very limited amount of space, I might need something like this or a thermistor than something like this. When we go to choose the instrument, we are now concerned about the actual property that we're measuring rather than the ultimate result. So are we measuring resistance? Are we measuring current? Are we trying to do IV characterization? Once we know that, then we can ask what kind of instrument can make that measurement. And it's important to note here that that includes more than just the measurement function, but also the levels that we're trying to measure. A digital multimeter is a great all-purpose tool, but it's not optimized for low current, for really sensitive measurements. And so just because it can measure current doesn't mean that it's the best option for our measurement. We may need to consider a sensitive measurement if that's what our sensor is requiring. Some instruments do come in with built-in sensor options. Most standard bench DMMs come with preset temperature measurements, so I can just connect my temperature sensor and configure the settings, and the instrument will convert all the data and take the measurement for me. But sometimes that isn't possible. So it's a nice to have, but not all the time. You need to consider whether or not you need a source. DMMs do have built-in sources to measure resistance, but sometimes that's not high enough current, or it might be too high of current, especially if we're doing IV characterization. We need to be able to sweep, and so we're looking at potentially a separate power supply, or one that's got power supply and measurement capability built in, like a source measure unit or SMU. The number of terminals in your sensor does affect the instrument we choose, especially if we're doing IV characterization. We may need multiple sources to source points on multiple terminals. And then a lot of times, sensor measurements are not single measurements. We are working with a lot of different sensors. For example, like if I was going to measure humidity in a lab, I might want a humidity sensor in all four corners of that lab to get a full sense of the room. So when we're working with more than one sensor, we might want to look at an instrument that can do that, and that would be the data logger. So what is a data logger? I like to think of it as a multi-channel DMM, but it is not true parallel, not true multi-channel. It's still sequential measurement. But on a data logger, you have built-in switches that are most often in a multiplexer arrangement, or sometimes we'll call them MUX cards. I have a simple diagram of what that looks like, but basically it connects multiple devices. For our DAC 6510, that would be up to 80 two-wire devices. For our 3706A, that's 576 two-wire devices. And then the switches will close and route one of those sensors to the DMM input to measure. The perks of data loggers are that they save time connecting and disconnecting your devices, and they're designed for long-term testing. Again, with sensors, oftentimes we aren't looking for just a single measurement check. We're looking to monitor trends and behavior changes over time. So sensors are so necessary in our society. They're often integrated into other systems and other devices that are measuring it instead of using a dedicated measurement instrument. I think it'd be really neat if every single car out there had a Keithley DMM built in it to measure temperature, but that's not actually reasonable. So in those cases, the process to decide how we're measuring it is not that much different. We still need to measure the value, interpret the value, and return the value where it needs to go. Either that's to us or to some other part of the system. And we still need to consider how the sensor is working, the number of terminals in it, levels being applied and measured. So all of that stuff still applies, even if we aren't choosing a dedicated measurement instrument. So if I had to pick a point in the process of using a sensor that would be the most critical, I would probably have to say it's this step. Connecting your sensor correctly and configuring your measurement correctly is necessary, or else your measurements don't mean anything. They are garbage. So remember that sensors are working on the relationship between one property and another. And if we don't understand that relationship, we can't make good measurements and we can't interpret our data correctly. So we need to know where the output of the sensor is being generated and how that is being connected to the circuit. If it's a voltage measurement, we need to know what's high and low, because if we connect it backwards and we get a negative reading, that might translate to bad data later on. Sometimes it matters where in the circuit the connection is made. This is a very, very common issue for thermocouples. I get people all the time that come to me and say, my thermocouple measurement isn't working. And my first question is always, where is your cold junction? So for a thermocouple, it matters because we have to understand what the temperature is at this end is the reference to measure this end. Where we have placed this end in our circuit, whether that's internal to a switch card, whether that's out in the lab somewhere, we need to know what this temperature is. It needs to be correct. Otherwise, everything is going to come out wrong. So that is very important. And also, we need to consider where we're placing the sensor in order to measure the property we want to measure. Lots of sensors involve conductive elements. Again, going back to our thermocouple, it's just a wire. So if I accidentally take that wire and touch something that is conducting, I could get errors. If we're measuring something liquid, are we protecting the sensor from being damaged if we have to replace that sensor in the liquid? Does the sensor need to touch what we're measuring? Does it need to be aligned in a certain direction? All of these factors matter, and this is why sensor measurements can get very complicated very quickly, because it matters how we are setting up the system. So we've made it. We are finally ready to take our data, and we've got measurements, but there's actually one more step we have to do that we cannot ignore, which is we have to convert the data that we took back to the measurement that we actually want to have. Some instruments will do this for us. If we have a built-in mode, they'll do the math for us and give us just the temperature data or what have you. Some instruments have built-in math capabilities, so we can input our conversion there, and then they'll do additional math. But sometimes we have to take the data and put it in a separate place and do the analysis separately. In order for us to do this, we have to know what the relationship is. It could be a mathematical equation, it could be a lookup table, it could be a graph, and we need to understand, is that relationship always the same across the operation of the sensor? Sometimes the relationship will get less accurate when you get closer to the extremes of the sensor capabilities, and there may be a specified change that we can make, a temperature coefficient or some other type of coefficient that we can include to account for that. Most often, this information is located in a data sheet, but for a lot of things like thermocouples that are very standard and are dependent on material properties, it may not be specified. It may be a generally known relationship that there will be a standard for. So you can find the information that way. And then the other thing we have to consider is what other constants or information do we need to know? Any kinds of material properties, coefficients of operation for sensors are usually, like I said, found in the data sheet. But sometimes we also need a reference value as part of our setup. That could be the resistance at the start of the test. That could be a reference temperature. And so we need to make sure that we have that data before we go and complete our test, because if we collect all our data and we walk away and we take down our system and then realize, oops, we needed a reference value, we don't have that system set up anymore. So we want to get the most out of our sensor measurements. Here's a few considerations that you can make when you're taking those measurements to try to get the best measurement possible. If your sensor involves low resistances, you should consider using 4-wire connections to remove any errors due to lead resistance for the measurement. This works by splitting the current source from the voltage measurement. The voltage measurement is a high impedance measurement. No current flows on those leads, and we've eliminated the lead resistance from the measurement, which is why RTDs come in 3- and 4-wire versions. So that's one thing you can do. Avoid using dissimilar metals in your connections because that can cause thermal offset errors if you're measuring low resistances, low voltages. I do want to give that a little caveat there that doesn't count for thermocouples. That thermal offset error from dissimilar metals is actually the property behind thermocouples, so we don't want to avoid that there. We actually want that to happen, but other things not so much. And then finally, you can also use the rel function of your DMM to help zero out any instrument errors. If you're measuring low current, consider using high quality cables that involve guarding and shielding that mitigate noise, and consider the need for sensitive instruments, especially low current is difficult to measure. Using a sensitive instrument that's optimized for that will give you a better performance. So we've got a number of application notes on our website on using sensors. I've highlighted a few here that happen to cover all of the measurements and sensors that we covered today in this session. So if you're interested in understanding any more about sensor measurements, all 4 of those are great resources to check out. So with that, I want to say thank you all so much for attending, and I hope you are now ready to go out and start measuring our world.
All right. Thank you so much, Liz. That was fantastic as usual. All
Thank you.
right, everybody, if you have questions, feel free to submit them into the questions tab. We did get a couple while she was presenting. Liz, are you ready to answer some questions?
I am ready.
All right. So I think this one comes from you talking a lot about temperature sensors. Carmen would like to know what are the standard sensors supported by a DMM?
So that's a great question because DMMs are one of the best tools to use when you're measuring sensors. So most commonly, they're supporting temperature measurements. A basic DMM might have a single thermocouple type or like a basic thermocouple and thermistor. A more advanced DMM, like the DMMs that we supply, will have your full selection between thermocouples, thermistors, and RTDs, and all kinds of different types of those built in, and sometimes even the ability to add your own custom.
Okay. All right. So our next question comes from Abdul. They say that they noticed the button on their DMM, REL. I'm guessing that doesn't mean real, but what does REL on a DMM mean?
So that is the rel function for relative offset. And when you use that function, basically the DMM takes a measurement, which is considered a zeroing measurement. And then every subsequent measurement afterwards, that first measurement will be subtracted. So you'll want to disconnect your sensor from the DMM when you're using this so that you're measuring just the offset of the DMM itself, any errors that might be there. And then if you're doing a voltage measurement, you'll leave your terminals open. Current measurements, it's with the DMM terminals shorted so that you're measuring almost zero. And when you enable rel, then the DMM will be measuring very close to zero. It'll be subtracting off all of those offsets and therefore subtracting any errors from your sensor measurement.
Okay. So James has a follow-up. Is rel the same thing as making a 4-wire measurement with a DMM?
It is not. So rel, like I said, is just subtracting a simple offset, but a 4-wire measurement is actually eliminating errors from your lead resistance. So if you're measuring a very small resistance, you're going to be generating some little voltage offset from the resistance of the leads themselves. And then if you're using 4-wire measurement, you're basically eliminating that voltage drop. I think I said voltage offset before, but voltage drop from the lead resistance.
Got it. Okay. I see the difference. Okay. Ben would like to know if they need a source for their sensor, what are some of the options that are available?
Well, your most basic option is going to be a power supply. You have lots of options with power supplies, but you do have to keep in mind they are primarily voltage sources and they aren't optimized for measurement necessarily. They do make measurements. They will be able to measure the current that they are outputting. But if you are trying to measure a lower current or measure current with high accuracy, you'll probably want to look at an instrument called a source measure unit or SMU. They can act as a voltage source or a true current source, and it is also a precision measurement instrument at the same time. So it's really great for doing things like sweeping lots of different source values and coordinating measurements with your source. So that is a really great option, especially if any of your sensors are kind of semiconductor device based, like a MOSFET. Those are perfect devices for SMU use.
All right, that's good to know about those.
Mhm.
Okay, so Matthew asks, in the context of guarding and shielding, how do you define guarding?
Ooh, that's a I could do a whole webinar on guarding just alone. So a guard, when we use like a triaxial connection, that inner conductor is what we consider a guard. And in many cases, that guard is driven to the same potential that the high pin is. So that's that center conductor. And what it does is it prevents kind of similar to well, I guess I'll go walk that back. It's not similar to four wire, but it's also eliminating errors. So when you have a high voltage and a low voltage, you're going to get leakage current between that. And when we have a guard that's the same potential as your high terminal, you are going to reduce the amount of current leaking across any insulation resistance in there. So that is especially important when you are doing low current measurements because you don't want to have your current leaking through your insulation resistance and then you're getting incorrect measurements.
Yeah, actually, now that you've explained that, I've read through some things a few times and it finally clicks.
Yeah.
So,
Not to be
so
confused with shielding, which is that outer conductor, which is actually helping remove any errors from external noise sources, like electromagnetic radiation and things like that. It's very
right.
much an external protection versus guarding, which is more of correcting potential internal leakage.
Okay, cool. Well, thanks for explaining that.
Yeah.
All right. We are at the end of our questions. Are there any closing comments you want to make, or are we?
No, thank you all for joining, and I hope you got a lot out of it.
All right. Thank you for presenting, Liz. Thank you for everyone that joined. Remember, this is part of a series, and we'll have the next one available soon. Thank you, everyone.
Thank you.